This is a lesson on the basis of science. Doing science. Scientific method is not linear. Method is not linear. It's a web. Sometimes it's not nice and neat. They teach you the idealized scientific method where you do step 1, step 2, step 3, step 4. In real life, you might jump in and step 3. It's a web. In your textbook, they have a web of things where you can go around gathering data, hypothesis, design labs, things like that. So lots of different ways of going about scientific method, and a lot of the biggest discoveries have been discovered by accident. They were looking for A and they found B, like penicillin, for example. There are two different types of experiments. There are experiments to find relations, study relations, like if I do this, what will happen to that? If I increase the pressure, what will happen to the volume? If I increase the amount of salt, what will happen to the temperature, boiling point of the temperature? So this is occasionally the if something, then something type deals. There's also relationships to determine values. You're just trying to find out what the density of this unknown metal is. You're trying to find out what the boiling point of water is. You're trying to find out what the different solubilities of different solutions are at different temperatures. So all you're doing is determining numbers. And they require different types of experiments to do each. Variables and constants. And constants. The independent variable is what the scientist can alter. He's in control of, or she's in control of. It's the variable I control. I can adjust what temperature the experiment is going to be done at. I can adjust what's the concentrations of the solutions. I can adjust the pressure that the experiment's done on. So the independent variable, I, is a variable I control. The dependent variable, that's supposed to be variable here. The dependent variable is the variable that you're trying to find. It's the value at the end of the experiment. It's the answer, if you will. So the dependent variable is the answer to the question. The independent variable is the variable that I am adjusting, changing. All factors except for these above should stay constant. You vary one independent variable at a time, and you find out what the dependent variable is at. So it should stay constant. As you do this, in science, in chemistry and physics, it's very easy to control all the different variables. Sometimes, like in biology, you might need a control. A control group is something that you do nothing to. Kind of ridiculous in chemistry to see what happens when you don't boil water. It sits there and does nothing. But in biology, you have different factors: humidity, light, growing seasons, pests. You just cannot control every possible setup. Now, occasionally we do something in chemistry on a control, like if we're studying color change, we'll do something with no variation. We can compare it to that control setup. So control is a set where nothing is a set of data, set of situations where no change is made, or the same changes as the other ones occur, except for the independent variable. Prediction and hypothesis. Prediction is a guess or estimation of what might happen. It's just a straight prediction. The water will boil at 105 degrees or something like that. A hypothesis is more involved because it has a prediction plus a reason. Many times, hypothesis will have the word because in it. If you design a procedure, a procedure should be designed and logical, well written, and this is a problem that students do. They just kind of assume too many things. You should be able to have so that others can follow your directions. It has to be detailed enough so that if you hand your procedure to somebody else, they can follow your directions and not go any, I don't understand what you're trying to do there. And it has to have the better ones have multiple trials. Sometimes in a classroom setting, we don't have time to do trials, but the better ones would be that way. Gathering data. Gather data, there are qualitative and quantitative data to analyze, and we'll get that later. The key things you're looking for is precision, and accuracy. They are not the same thing in science. It might sound like precise, and accurate, same thing in real life. But in scientific reasoning, precision means repeatable results. It means that you get the same answer over and over and over again. You're not wildly varying all over the place. Both with very good confidence and repetitive confidence. You do it over and over again, you get darn close to the same answer. Accuracy means you are close to reality, or the real answer. The analogy people use in science is a dartboard. You can have all your shots be very close together, meaning you're precise, but you're not accurate, because accuracy means you hit the bullseye. Accuracy might mean you're on target. But if you don't do it once, you can't be sure if that's precise or not. And what the scientist really wants is precision and accuracy, close to this right answer and grouped up close together. Theories and laws. These are closely related to predictions and hypotheses. Both are generalizations based on many different experiments by many different scientists the world over. They both are highly regarded. Most people will agree on what's going on. A law is pretty much what a prediction is. It will say what will happen. The law of gravity. Items will fall towards the center of the earth. It doesn't tell you why it does it. It just says it does. A theory is like a hypothesis. A hypothesis is a one-shot deal. A theory is based on many different trials. Theory will tell you what will happen and why. The what and why. And again, it has the word because. Oftentimes in it, you can rephrase it different ways, but that's usually what it is. Predictions, hypotheses, laws, and theories, they all can be wrong. Many times in science, people have thought they had a law or a theory, and then more data comes in, and it's found out. So it can be wrong. Nothing is set in stone. So it could be wrong. You could have to change it. You got to be open-minded enough to do that. And if it's changed, it's based on new information, new data. A lot of times, bad things in science happen because people get stuck in their ways. They're not open-minded enough to say, well, look at this might be different. Communication. Scientists make a big deal about communication, about what your procedures are, what your results are, so that they can be backed up by others. So share information about procedures, about theories, about predictions. And this also allows others to verify. So one person doing it is a hypothesis, many people doing it through communication, through scientific journals and whatnot, will let people come up with a stronger statement of theory because it's backed up by other people independently. Now there are some times where you don't want to do communications, like if you're in the military, you don't want to communicate data and information there. If you're a business, you don't want to give out information there. But as far as pure research, communication is vital. That ends this lesson on doing science.